My name is Shiyu Suzuki. I'm from Japan Aerospace Exploration Agency. And I firstly apologize that this is the sudden interruption in the original conference schedule. So I'm sorry for this. And today's topic is effect of temperature on mechanical properties of additively manufactured ALSI. Actually, I'm not sure how I can pronounce this, but ALSI magnesium alloy and its lattice structure. But basically, today's presentation focuses on lattice structure mechanical properties. This is the brief background of additive manufacturing. As the previous presenters explained, the additive manufacturing can manufacture parts or components with complex geometries that are not manufactured by conventional machine technologies like something like this. And it also can control material properties and add functionalities by tuning manufacturing parameters. And also it holds a better rate of material consumption. Because of this, the additive manufacturing is becoming very popular. And one application of AM technology is the lattice structure. This is the schematic diagram or schematics of the lattice, various types of lattice cells. Apparently these are the lighter. It's light compared to bulk materials, and also it can add damping performance or tune Poisson's ratio and anisotropy by optimizing cell structures. So a lot of engineering companies or research institutes is trying to apply these lattice structures to, for example, aerospace components like rocket engines or jet engines, or aerospace wings or fuselages. So these are the different types of the examples of application of lattice structure in aerospace. So for example, we can see that this is the support for the cryogenic tank, and this is the airplane wings, and this is the supersonic airplanes, which needs to be very light compared to the conventional airplanes. And this is engine components, and different components needs to be operated under different temperatures, such as this is 100 degrees Celsius, minus 50 degrees Celsius, and 200 degrees Celsius. And engine components must be tolerant higher than 1000 degrees Celsius. But the current problem is that although a lot of people are trying to apply these technologies, mechanical properties of lattice structures at low and high temperature have been rarely investigated. And frankly speaking, in the range of our previous paper survey, there is no previous studies, for example, regarding fatigue properties of lattice structures. So the aim of this study is to investigate the effect of temperature on mechanical properties of the additively manufactured lattice structure, especially focusing on ALSI magnesium alloy. So this is the experimental procedure. We used ALSI magnesium alloy, which is manufactured by laser powder bed fusion. The machine we used is EOS M290, and these are the manufacturing parameters. And the one important thing is heat treatment. This is for relieve the residual stress. So we prepare two types of specimens. One is cylindrical specimen, which is normal based on the STM standard. The other is lattice specimen. So lattice specimen consists of multiple unit cells. Unit cells we used is simple cube, which have 3 millimeters in each direction, and the strut width is 0.5 millimeters, and the ratio of the density of this unit cell compared to the bulk material is 0.26. So we aligned these unit cells in actual direction 6 unit cells and 10 unit cells and 10 unit cells. And we can also see that there is a gradient lattice to reduce the stress concentration between bulk materials and gauge sections. And we manufactured all of the specimen in one build plate. And these are the experimental procedures. This is the testing machine we used, which is basically based on the instruments of hydraulic machine, but with the environmental chamber. And we also use extensometer of the gauge length of 50 millimeters. And we conducted two types of tests. The one is static tension, the other is fatigue. And for the static tension, we only use lattice specimen at different temperatures from room temperature to 200 degrees Celsius. And for the fatigue test, we applied the load ratio is 0.1 and 10 Hertz, and we set run out at 10 to 7 cycles. And we used 3 cylindrical specimen at room temperature. These are the stress conditions. And we also use lattice specimen at room temperature. We conducted 3 tests. Some of them is conducted under the same stress condition with the cylindrical specimen. And we also conducted lattice fatigue test at 200 degrees Celsius. And some of you may consider that what is the stress condition in lattice specimen, because there's a lot of stress concentration in lattice structure. So in this presentation, we basically based on the nominal stress, which is calculated by the minimal cross section in the axial direction. So this is the result. This is the lattice stress static tension test. The blue is -60 and black is room temperature, and red is 200 degrees Celsius. The vertical axis is load, and the horizontal is displacement. So by decreasing room temperature to -60 degrees Celsius, the strength becomes higher, but the ductility remains almost constant. But by increasing temperature from room temperature to 200 degrees Celsius, the strength becomes lower and ductility becomes higher. And when we observe the fracture morphology at room temperature and -60 degrees Celsius, there's only 6 single main cracks propagated. I'm sorry, for the room temperature, the crack opening is very thin, but there is only one main crack. -60 degrees Celsius it is apparent. But at 200 degrees Celsius, there's 2 main cracks, and the crack propagated with large inelastic strain. And this is lattice fatigue test at room temperature. The vertical axis is stress amplitude, the horizontal is fatigue lines. And we conducted 3 different tests with 3 different stress conditions. And this table contains all, the same data of this, figure. And right-hand side figure is the hysteresis curves with the static tension load displacement data. So from this, figure, we can see that there's only elastic deformation during the test under the all stress conditions. So we can apply the Baskin's law, which can be applied for the high cycle fatigue tests to the lattice fatigue tests. There is a good agreement between fitting and the experimental data. And when we look at the fracture morphology of the fatigue tests, in all of the stress conditions, there is only single main cracks in different types of tests, which is quite similar to the static tension tests. And each of the strut is fractured at the corner of the unit cells, which may be because of the stress concentrations. And when we compare this lattice fatigue test with the cylindrical data, there is a huge gap between them. The lattice fatigue lives are lower than 1/10 of cylindrical specimen, and this may be caused by these stress concentrations in the lattice structures. But these, contents or experimental results are not so unique. A lot of different, researches had been done before, this research. So what makes this presentation unique is this lattice fatigue at 200 degrees Celsius. The left-hand side figure is the SN diagram. We conducted 4 different, tests. And there is a runout at 14.5 megapascal, but the other had the definite, fatigue lives. And these are the hysteresis curves. As you can see, there is no areas in the curves, so we can say that we can consider that these are elastic, fatigue. Elastic deformation was dominant under all load conditions. However, when we see the fracture morphologies, we can get different insights because in the stress conditions lower than the 14.9 megapascal, we can see that there is single main crux in the specimen. But when we see that the specimen higher than 58.8 megapascal, there is 2 main crux, and we can see that there is an inelastic deformation, and this is quite similar to static tension tests. So we can say that these 2 types of tests are high cycle fatigue, but this type is low cycle fatigue. So we can apply the Bastian's law to these 2 types of data, and we can draw a fitting curve here. This runout specimen is lower than the fitting curve extrapolation, which is very reasonable. And when we compare this 200 degrees Celsius result with the room temperature result, there is a unique result. Because in the high cycle regime, the 200 degrees Celsius resulted in the higher fatigue lives compared to room temperature. But in the low cycle regime, the fatigue lives at 200 degrees Celsius is lower than the room temperature. And since we have not conducted any cylindrical specimen tests at 200 degrees Celsius, we try to find experimental data from the literature. And this is the excellent paper from Dr. Zheng Wan. They conducted fatigue tests using ALSI magnesium alloy with using flat specimen, and load ratio is 0.2 and 5 Hertz. And they they prepared different types of specimen under different scanning speed of additive manufacturing. But all of the data, the horizontal axis is the fatigue lives, and the vertical is fatigue lives, and horizontal is temperature. And all of the specimen show the decreasing trend with increasing temperature, which is quite different from our tests. So we consider that high cycle fatigue life higher at 200 than at room temperature in this study may be unique characteristic of the lattice structure. But actually, the reason for this is unknown currently. So further study is ongoing. So this is the conclusion. I'm sorry, it is too wordy, but I'm trying to pick up the only important things. So we conducted static tension test using lattice specimen. The decreased temperature from room temperature to -60 resulted in higher strength and equivalent ductility. And in increasing temperature from room temperature to 200 resulted in lower strength and higher ductility. And fatigue lives at room temperature of the lattice specimen the fatigue lives of the lattice specimen is less than 1/10 of that of the cylindrical specimens. This was attributed to the stress concentration at the intersections in the lattice structure. And the fatigue lives of the lattice specimen at 200 was very unique. Firstly, under low stress, which is lower than 14.9 megapascal, single main crux led to the fracture. But under high stress, higher than 15.8 megapascal, 2 main crux propagated as similar to the static tension test. So we can classify these 2 tests into high cycle and low cycle fatigues. And under low stress, lower than 40.9 megapascal, fatigue lives at 200 is higher than at room temperature. And this may be unique to the lattice structure based on the literature data. Thank you for your listening.